Hello, I'm Francisco Villalobos. I teach agronomy at the University of Córdoba and do my research at the Institute for Sustainable Agriculture of the Spanish National Research Council. I'm talking today about ClimaSG, which is a weather generator for crop modeling and water requirements calculations. This is not a new weather generator, but a modification of CIMETEO, where we wanted to follow the same objectives. First, try to reduce the problem of over-dispersion in rainfall data. Over-dispersion is the reduction in the variance of data commonly found for rainfall. We wanted also to add new weather variables, specifically wind speed and vapor pressure, which are required for calculation of evapotranspiration using combination methods. And we wanted also to simplify the acquisition of input data. This is many times necessary for education uses. So to use monthly values using CIMETEO from the CleanWatt dataset that includes more than 4,000 weather stations around the world. As I said, over-dispersion means underestimation of the interannual variance in monthly and annual total rainfall. This has been also observed for temperature, but the problem is basically more important for rainfall. The idea here is that the model used for rainfall occurrence will fix the interannual variability. CIMETEO and the parent system WG of Richardson uses a first order Markov chain for generating rainfall events, and that specifically will cause over-dispersion in general. From theory, we can relate the characteristics of the Markov chain to the variance to the interannual variance of the generated data. If we consider the distribution of monthly rainfall, we can calculate the mean of monthly rainfall as the product of the number of days in the month, the mean rainfall per wet day, P, and the fraction of wet days, F. With those values of N, P, and F, we can calculate the variance of monthly rainfall as the product of the number of days in the month, N, multiplied by a function where we found P, which is the mean rainfall per wet day, sigma sub P to the square, and this is the variance of rainfall per wet day, and D, which is the difference in transition probabilities between the wet to wet day and dry to wet day. So when we use a first order Markov chain, we can calculate, according to theory, what is the expected variance using this equation for the interannual monthly rainfall for a given month. Using the empirical equations of Genn and Penning-de Vries that showed that the transition probabilities of the first order Markov chain are related to the average frequency of wet days in the month, we can simplify the previous equation so we can calculate the variance of monthly rainfall as a function of n, which is the number of days in the month, f, the mean frequency of wet days, p, which is the average rainfall per wet day, and that's it. So it is very simple to calculate. Then, to get the annual variance of annual generated rainfall, we will sum the variance for each of the 12 months. In general, the variance of the generated rainfall will be lower than the actual value. So we would need to add an additional variance to get the actual variance, V2, and this increase in variance may be achieved by adding a low frequency component to the frequency of wet days that would have a variance according to this equation. In this equation, we only need to add the mean monthly rainfall and the mean number of days in the month. Where can we get actual values of interannual variation in monthly rainfall? We can go to a gridded, there are several, but we have used the gridded monthly global precipitation and temperature dataset with 0.5 degrees resolution of NCAR. So for any of the more than 1,000 locations of ClimaSG, we can get the actual interannual variance of rainfall and then apply the previous equations to include in the generation model this increase in variance. So we will come with a variance close to the actual value. There is a secondary correction. I only will mention it because the problem, or one possible problem in using CMeteo or similar models like WGen, is that the generation of rainfall and temperature are done independently. Specifically, in general, we have a proportionality between solar radiation and the range in temperature between the maximum and the minimum value. So we have included in ClimaSG, we have included a correction so the generated values of solar radiation are associated to the variations in the difference between Tmax and Tmin. ClimaSG doesn't have values of vapor pressure or wind, and we have included those variables first in the case of vapor pressure, assuming that the mean daily vapor pressure is proportional to the saturated vapor pressure at minimum temperature, ESN. So we will generate for each day of generated data, we will generate mean vapor pressure proportional to the value of saturated vapor pressure at the generated mean temperature multiplied by a coefficient that requires knowing the monthly mean vapor pressure. This is the only additional input for the weather generator. And then ES and M would be the saturated vapor pressure at the mean minimum temperature. In the case of wind speed, we have used the Rayleigh distribution. The advantage of the Rayleigh distribution is that we can use it knowing only the mean wind speed during the month. So we will generate daily values of U, of wind speed, using the inverse cumulative distribution function like this, using this equation, where UM is the mean monthly wind speed and R is a random number from a 0-1 uniform distribution. We have tested ClimaSG first doing a comparison with actual data and then testing the generated data for simulation with a crop simulation model or for calculation of ETO, which is very important in calculating crop water requirements. The comparison with actual data has been performed first for rainfall and temperature using the NOAA database, where we have used the criteria of getting all the stations of the CleanWatt database that have more than 90% of the data in the period from 1988 to 2017. We found more than 500 stations that met those criteria. We have also taken data from complete stations for calculating with Penman-Monteith, the 4 stations having daily values of solar radiation, air temperature max and mean, vapor pressure and wind speed. And we have collected data from 45 stations in Spain, from the SIAR system. Those stations had on average 15 years, and then from California, from the CIMI system, we collected 13 stations at different counties, and we had an average of 30 years of data. For crop simulations, we use the data to feed OliveCAN, which is a crop growth and yield model for olive orchards, and we use that the model only in areas where olive is grown. And we tested the calculations of ETO in all complete stations. The system was tested in the case of temperatures using according to different possible variables, like the absolute minimum temperature in the year, the absolute minimum year temperature in 10-year periods, the date of the first frost or the last frost, and the actual mean monthly maximum or minimum temperatures, also for the frequency of frosts. The statistics were quite similar to CIMETEO, as the statistics have not been changed for temperatures as compared with CIMETEO. That was not any objective of our new program. But here you can see that for some variables, for instance, for minimum temperature, absolute minimum temperature, the errors can be important. That is something that we have to take into account. The same goes for CIMETEO. So in that, the same problems are still there. But when we test the weather generator for rainfall and we do the comparison for the standard deviation of monthly rainfall, when we compare CIMETEO with ClimaSG, we see a much better performance of ClimaSG, as the slope of this standard deviation of monthly rainfall between generated and actual rainfall is close to 1, and the intercept is very, very low. The mean bias error is close to 0, while the mean bias error is important in the case of CIMETEO. This is an indicative, this -88 for CIMETEO shows how important the overdispersion phenomenon is in this case. So ClimaSG has been successful in removing basically the overdispersion problem for monthly or annual rainfall. For ETO, here we have the comparison of the actual values of for the month of July, which shows the highest values in California and in Spain, and we see that the standard deviations of ETO and the mean values are very close to each other. So ClimaSG is quite capable of producing the average and variance of ETO for the peak period in the summer in California and Spain. If we consider the root mean square error for the maximum monthly ETO, the value is very small, both in Spain and California, and when we evaluate the 95% probability level for daily ETO, the error is 0.6, around 0.6, 0.7, which is more than reasonable. It's less than 10% of the mean value. So we can conclude from the tests of the weather generator that the problems with extreme temperatures are still there, and those are shared by CIMETEO, that the generation of wind and vapor pressure was satisfactory, that the rainfall variability has improved substantially over CIMETEO, that the generated ETO with ClimaSG is statistically equal to the actual values, and we have found problems when running long simulations with the OLIVE model, that the occurrence of very low generated temperatures might cause problems because of defoliation by frost. But the same problem would come if we use CIMETEO for that. In any case, if we want to simulate olive orchards using generated data, we have to say that it would work okay in static mode. That means that the orchard is reset every year, so we are always simulating the same orchard. The software is free for download from our webpage, ClimaSG, at the University of Cordoba webpage. We have versions in English, Spanish, French, and Portuguese, and we have also included tutorials for the users. The program is very easy to use. First, we have a form where we select the country, and within each country we will have a list of weather stations. We select one. Then we have a second part where we can change the temperature or the rainfall if we want to add a perturbation. For instance, in studies for climate change, we can add the same perturbation for the whole year, or we can use perturbations specific for each month of the year. Then we select the number of years that we want to generate, and then we click and we will get the generated values. Apart from generating the daily data, the program will analyze the data, calculate the ETO, and will show, if we want, the variation throughout the year of ETO, average temperature, rainfall, or even the frequency distribution for the probability of frost in the autumn, the first frost, or the last frost in spring. Apart from that, apart from taking data from the CleanWatt database, we can create additional stations. In this form, we will add solar radiation. We can also copy those from an Excel file with Tmax, Tmin, rainfall of the month, number of rainy days, wind and vapor pressure. So we can add new stations to generate data in additional places. The generated files are first in our regular format that includes solar radiation, extreme temperature, rain, wind and vapor pressure. We can also select between the format between US or European format. Here we have an example of European format. And we also generate, the data are also generated in DSSAT format, as you can see here, for the same dataset. Thank you very much for your attention.